input parameter characterization for as-built Ti-6Al-4V additive manufacturing. Additive manufacturing has come to mean the process of creating three-dimensional parts by fusing material layer by layer. This differs from casting because not all the material is added at once. It does not require a mold. There is minimal possibility of cold shuts, washes, and misruns. Additionally, there is likely less post-machining required for AM processes. The layering technique also allows for complex geometries which can lead to more weight-efficient parts. There are other benefits to additive manufacturing, chiefly the ability to rapid prototype. The lack of a mold makes one-off part production easy and quick. There are drawbacks, however. Limited material choices, high energy consumption, and understanding of as-built material behavior are all issues which need to be addressed. There are multiple 3D printing techniques, but for this project, a process called direct metal laser sintering, or DMLS, will be covered. In this process, metal powder is laid down, then fused together through the use of a laser. There have been some studies which have paved the way for understanding of the additive manufacturing process and how input parameters affect the material properties of the components. Studies have found that build orientation is key to part strength and is often among the most influential parameters. The importance of orientation as found by these studies shows how impactful the amorphous, nonlinear characteristics of as-built components are. Then there is the more obvious input parameters for DMLS, that is the laser settings. The scan pattern, the laser intensity, and the scan speed are all influential parameters on component strength. For example, one study found that residual stresses can be reduced significantly by rotating the island orientation 45 degrees and reducing their size. Additionally, the laser intensity should be increased as the number of layers increases due to the increased thermal mass, which would dictate higher temperatures required for layer-to-layer fusion. Other parameters have trade-offs. For example, the higher interface temperature, the higher the density and ultimate tensile strength of the part. Unfortunately, this gives you a lower yield stress. Other studies have found that changing the particle size or even mixing particle size would reduce the need for increases in laser power. After reading over the related work, the objective of this project became clear. Through parametric study, the tensile strength, yield strength, elastic modulus, and ductility of as-built DMLS components will be found. The parameters to be varied will be the most influential: heat source power, heat source travel speed, and build orientation. To be delivered as a result of this project are the physical test specimens and the data which will be collected as a result. Accomplishing these tasks will require the design of specialized test specimens which fit the intended test machine and meet ASTM standards. Additionally, the standard operating procedure will need to be developed to obtain consistent results. After parameter adjustment, resolution will need to be determined and the sample sets printed. Finally, the samples will be tested and the appropriate data points extracted from the stress-strain curves. Using this data, the multivariable regression models will be generated. This last deliverable is the most impactful as it can be used to predict material properties of components produced using this process. The methodology is straightforward. First, the dimensions and standard operating procedure for the specimens will be defined using ASTM material testing procedures. The initial specimens will be tested to ensure they produce usable data. The specimens will then be printed and tested on an electromechanical universal test machine, from which the stress-strain curves will be generated, using the onboard sensors. The desired data points will be extracted and calculated and put into a digestible format. The tested samples and collected data will be submitted for review by committee. Next, the multivariable regression models will be produced using the data collected and the statistical analysis performed. To evaluate the results, the raw data will be analyzed for process repeatability. This will come in the form of sample variance and a standard deviation of the sample sets. The smaller the variance and standard deviation of each set, the more repeatable the process is. This will take place for each sample set, and so track the repeatability as the parameters are swept through their range. The other evaluation metric for the regression models will be the R-squared value associated with them. The smaller the residual sum of squares, the more one can say that they are representative of reality, and thus relied upon for design. The largest anticipated challenge for this project is the amount of time it will take to do all of this. Even if the samples are print exactly as expected, test exactly as expected, and there are no machine failures, the time required to print, test, and analyze each sample will still take a tremendous amount of time. To alleviate this time requirement, I will begin the project well in advance of the official start date. An initial design for the test specimen has already been created. Its dimensions are derived from ASTM standards and basic definitions of stress. The values of the stress have been taken from similar studies of the subject for similar materials. Part of the project is ensuring that the data collected is significant and usable. Using the equation shown, the standard deviations from similar studies, and the desired error, the required sample size per parameter variation, and the total number of samples can be found. Based on the previous calculations, approximately 20 pounds of material will be needed for the samples themselves, ignoring waste and mistakes in printing. In addition to the tangible resources needed, I will need access to some software packages and the machines for testing. The project poses some intellectual challenges. For example, the project covers nonlinear anisotropic properties of test specimens, a topic which extends beyond the basic material science. It will require analysis of microstructure of the test specimens so that basic explanation for material behavior can be provided. Additionally, there will be statistical analysis of the results coupled with multivariable regression models, all of which covers material not explored by a bachelor's level education. The impact is also significant. Additive manufacturing is a new technology which offers benefits over existing techniques. Its newness requires a further exploration into its behavior. Parts produced by this method can potentially save on manufacturing costs, make more efficient parts, and change our approach to manufacturing.